How many grams of oxygen are required to react completely with 10 grams of iron? Yep. What do we get?
14.58.
We get it back then?
4.3.
4.3? Yes.
4.30.
Good. All right, so we can set up our ratio. What's given is the iron. So in the numerator, we're going to use everything about the iron. So the stoichiometry 4 from the equation times the molar mass of iron. We're going to put that over the 10 grams of iron that's given in the problem. Now this time it's asking about oxygen. So over here we're going to use our 3 moles of oxygen times our 32 grams per mole, which is the molar mass of oxygen, and we're trying to find grams of that. So we're going to cross multiply and divide, and you should get 4.3 grams of O2. So again, this ratio works when you're going from grams to grams. Now, if the question asked you how many moles of oxygen are produced, how would you solve it then?
How many moles of, that's just, I go back a step. Sorry, it was 0.1344.
Okay, so you did it the 3-step way. That's fine, which I'm giving 2 different options so that you can use what you like, what works for you. So if the question were to ask how many moles of oxygen are required to react completely with the 10 grams, you could still do this, but then you would convert back to moles using the molar mass. You would get the 0.13 and some change moles of O2. The other thing that should work if you wanted to still set up this ratio, if we were trying to find moles of O2, if you're just finding moles of O2, you should be able to still set up this ratio, but leave out the molar mass part. You would just put in the 3 moles of the O2, cross multiply and divide, and that should still work.
So just put the coefficients?
If you're finding moles. If you're finding grams, then you've got to put in the molar mass too. But if you're only going to moles, then you would just leave that part out. All right. So I want to expand upon this. And talk about the next type of problem, which are called limiting reactant problems. So last week when we were introduced to stoichiometry, I asked you to define the word excess. Okay, and we said that excess meant a lot, extra, plenty of. And all of the calculations that we've done so far have been in excess of the other reactant. So the way these were written this morning, you know, how much iron oxide is produced when however many moles of iron react completely. So you're assuming all the iron reacted and had plenty of oxygen there to react. Well, with a limiting reactant type problem, now you have certain amounts of each type of reactant in the equation. So let's look at this reaction here. I've got 2 moles of nitrogen monoxide gas reacting with 5 moles of H2, and that produces 2 moles of ammonia in H3 and 2 moles of water. .3 grams of nitrogen monoxide is allowed to react with 25.6 grams of H2. What is the mass in grams of NH3 produced? .3 grams of nitrogen monoxide is allowed to react with 25.6 grams of hydrogen. And we want to calculate what is the mass in grams of NH3 produced. All right, so what's similar about this problem is that we're given grams of the substance in the reaction, and we're trying to find grams of something else in the reaction. What's different is that now this time we're given grams of both reactants. We're given grams of nitrogen monoxide, and there's a certain amount of hydrogen. So the difference here is not one of these is in excess. Okay? we have fixed amounts of both reactants, so this reaction is going to occur, and eventually one of these reactants is going to run out before the other. When the reactant runs out, the reaction stops. Okay, so one of the analogies that I sometimes make when I'm teaching limiting reactant is making turkey sandwiches. Okay, if I've got 10 pieces of bread and 10 pieces of turkey, and I want 2 pieces of turkey, nope, that doesn't work. If I have 10 pieces of bread and 6 pieces of turkey, and I want 2 pieces of turkey on each sandwich, I run out of turkey before I can use up all the bread. I can only, according to my 6 pieces of turkey, I can only make 6 turkey sandwiches. Did I say that right? According to my 6 pieces of turkey, I'm glad I'm recording this. 6 pieces of turkey, I can only make 3 turkey sandwiches. But based on my 10 pieces of bread, I have enough bread to make 5 sandwiches, but I run out of turkey before I can make 5. So that same idea applies for the chemical reactions, where when these substances react, once one of the reactants runs out, the reaction stops. We can't make any more product without that reactant there. So what we have to do is now calculate the mass of ammonia formed based on each amount of reactant. So now you're doing your stoichiometry problem twice. The first time using the grams of NO, and you're finding grams of ammonia. And then you're doing that same calculation again using the grams of hydrogen to find grams of ammonia. So I think everybody likes this ratio, so I'll start with the grams of NO. All right, so the substance that's given was the nitrogen monoxide. So in the numerator of my ratio, I'm going to use my stoichiometry 2, and then I'm going to use the molar mass of NO. So I get the molar mass of NO by finding the molar mass of nitrogen and adding the mass of 1 oxygen. 30.01. And then what I'm trying to find is the ammonia, so I'm going to use the stoichiometry of the ammonia, and then the molar mass of the ammonia should be about 17.03. Right? Then what goes in the denominator is the actual amount given. Here's our x. So when we cross multiply and divide, we should get 86.3 times 2 times our 17.03 divided by our 2 times 30.01. And then we're going to do this same calculation using the 25.6 grams of the hydrogen. I think that I'll have room over here. So for the H2, I'm going to use the 5 moles of H2 times the molar mass of H2, which is going to be 2.016. Again, what we're trying to find is the ammonia, so the NH3 is still what's going to be over here. Okay, so all we've done is we've taken the grams of NO and we've calculated the grams of NH3 that can be made based on this amount of NO. And then we've taken our grams of H2 and again we found how many grams of NH3 can be produced based on this amount of H2. So we have two answers here. So what we have to do is compare these two numbers. The theoretical yield is going to be the amount of product that can be formed, and it's the lower amount of product. Okay, so our theoretical yield is this 49 grams of NH3. Okay, that is in theory the maximum amount of ammonia that can be produced based on these amounts of reactant. The limiting reactant is the reactant that limits how much product can be made. It's the reactant that runs out first. So what is our limiting reactant here?
The 25.6. Wait. I'm sorry, I was looking at which board, sorry.
Yep, that's okay.
86.
It's our 86.3 grams of NO. So the nitrogen monoxide is our limiting reactant. Okay, so for this problem, the limiting reactant was our nitrogen monoxide, and the theoretical yield was our 49 grams of NH3.
I have a question.
Yes.
So based on this problem, the limiting reactant, which is nitrogen monoxide, also produce a theoretical yield. Is that true for every problem?
Yes.
Okay.
Yes, the limiting reactant is always the one that is the one that you base your theoretical yield on, because the limiting reactant is the one that produces the smaller amount of product.
Gotcha.
All right, so to drive this point home, can you determine the limiting reactant just based on looking at the amounts given in the problem?
No. Okay.
No, because here you've got a much smaller mass of hydrogen, but it is not the limiting reactant. Okay, if you just compare these two numbers, it looks like you'd run out of hydrogen first, but you don't. Hydrogen actually makes about almost twice as much product compared to the NO. The reason for that is because hydrogen has a much smaller molar mass, and you've got to account for the stoichiometry of the reaction. So you can't just compare the masses given in the problem. You have to calculate mass of product. Let's do another example. what is the theoretical yield in grams of titanium when 28.6 grams of carbon react with 88.2 grams of titanium dioxide? And then also answer, what is the limiting reactant? About 1 more minute. Does anybody have a theoretical yield? What about a limiting reactant? The TiO2? Titanium oxide?
Yes.
You get that? Okay. All right, so we'll start with our carbon. And so we'll set up our ratio. We had 2 moles of carbon. Carbon is 12.01 and some change grams per mole. And we're trying to find grams of titanium. So our stoichiometry is 1. The mass of titanium is 47.87. That's what we're solving for. We're given 28.6 grams of carbon. And when you cross multiply and divide here, you should get 56.6 grams of the titanium. And that's based on the amount of carbon that's given. Then if we do the same calculation using the amount of the titanium oxide, we're going to use our 1 mole of titanium oxide, the molar mass of titanium oxide, which is 79.87. We're given the 88.2 grams of that. Again, times our 1, which is 47.87 grams per mole over X. So again, when you do this, the second one, you're still finding grams of titanium. And so you should get 52.9 grams. Of titanium. So our theoretical yield is our 52.9 grams of titanium, because this is the smaller amount compared to the 56.6 grams. So our theoretical yield is the 52.9 grams of titanium, and our limiting reactant was the titanium oxide, because that is what produced the smaller amount. One more calculation before you go. Got 1 more minute. Let's suppose that you went into the lab and you were to carry out this experiment. Okay? This is the theoretical yield. In theory, this is how much you should make. But when you are actually working in the lab, sometimes reactions don't always go all the way to completion for other reasons besides limiting reactant. So let's say you did this reaction and you actually only recovered 42.8 grams of titanium. Say that was the amount that you actually got in lab. We can calculate a percent yield by dividing the actual yield by the theoretical yield. Times 100 to make it a percent, right? This actual yield is going to be a number that has to be given to you in the problem. All right, so that's just assuming, like, if you were in lab doing this, this is how much you recovered. So this has to be given, but the theoretical yield is what you calculate. So to calculate the percent yield for this one, we would divide our 42.8 grams by the theoretical yield, which is our 52.9 grams times 100, and that gives us an 80.9% yield. All right, so today we reviewed stoichiometry. We learned about limiting reactant, theoretical yield, and now percent yield. On Wednesday, we're going to talk about solutions. So